All right, so first let's look at this warm-up question. So let's suppose we have an ideal gas in a sealed container. So the temperature and the volume of the container are both increased. So what properties of the gas necessarily change? So hopefully this problem makes you think, oh, I need to think about the ideal gas law and what quantities can change based on the information given here. Okay, so hopefully you've decided that, well, if the temperature of the gas increases, well then for sure the kinetic energy of the gas increases. So this means that B for sure is correct. Thermal energy of the gas. So that will have to increase since temperature increases. And since temperature increases, that also means that the average speed of the gases also has to be higher. So A is also correct. C could be correct under some situations. We don't know, so it's not necessary that that's going to change. And then finally, the number of molecules, we know that actually is not going to change because it's a sealed container. Okay, so today we're going to kind of put some names to some simple processes, or processes. I'll probably say it both ways. So basically, we're going to look at a system of gas, and it's going to go through some changes in terms of its thermal properties, so pressure, volume, temperature, that kind of thing. And we're going to see and put names to the type of changes it can go through. So when I say a gas goes through a process, it means there's going to be some sort of change, and we're going to see how different parameters are affected because of that, right? So for example, maybe you wanted to kind of analyze how much our tire pressure increases as a day progresses. So as like the temperature in the air increases, and therefore the temperature inside the tire increases. We're actually going to answer that question specifically later. But we're going to kind of note the following things, right? So we're going to see that inside this tire, right, this is a sealed container, so the amount of gas doesn't change. So the number of molecules or number of moles, however you want to look at it, is not going to change. We also have a well-defined initial state, right? We're saying, well, our gas inside the tire starts with a certain pressure, a certain volume, and a certain temperature, and then it's going to reach a final pressure, volume, and temperature. So the change of this gas to some of these quantities to the other, where some of these might be the same, and that's okay, but we call this a process, right? An ideal gas process. Something that's going to be helpful for us is for gases in a concealed container, right? So if we're looking at the ideal gas law, the quantity of N times R, N times K, whichever ideal gas law you're looking at, is going to be constant. So that means that the quantity of PV over T is constant through the process, right? So it says for our initial state, PV over T is equal to that for the final state. So sometimes we'll have available to us a PV diagram, and on that diagram we'll have different states represented. So here we have one gas, so one system, but different points in time, so to speak, are shown. So we have state number 1 here, in which the temperature of the gas is 900 Kelvin, its volume is 1 meter cubed, and its pressure is about 7.5 kilopascals. Whereas at some other moment in time, state 2, it's at a temperature of 3600 Kelvin, a volume of 3 meters cubed, and a pressure of 10 kilopascals, and similarly for state 3, right? So the gas changes from one state to another, so these quantities change, and this depiction here, it does not really show us how the gas changes, so kind of how it goes from one state to another. It just shows us 3 different points. What's also nice about this graph here is actually it does specify temperature. That's not always going to be the case, like it is, for example, in this other graph here, where we're told some information about different states, but not here. We're actually not told the temperature. Sometimes we're able to compute the temperature given certain information. Sometimes we need to in order to actually analyze the problem fully. But for example, in graph B here, we've got our gas changing from state 1 to state 3. I don't know why they don't go to number 2 first, but whatever. And we can tell it goes through that change because here it tells us that we've got how it kind of transformed to that. So what happened to this gas is first it was kept at a constant volume and the pressure was decreased. And then once it reached, whatever this volume is, it was kept at that volume and the pressure was wow, did I completely say that wrong? I did, sorry. So first, the volumes kept constant and the pressures decreased, and then the pressures kept constant and volumes increased. Wow, I can't believe I read that wrong. Okay. But these arrows tell you the gas, started at state 1 and then it transformed through this specific method of process. So the first type of process we'll talk about is one in which the volume is kept constant. Right? So this is also known as isocoric, or sometimes it's also called isovolumetric. Right? So iso meaning constant or the same. So what we've got going on here, so we have a constant volume. So our gas is in some sort of container that cannot change its shape. So the amount of volume is always the same. So the way we could have, if you're looking at a PV diagram, volume is always going to be the same, but we can have a pressure change, right? So it's always going to be represented by the vertical line in the diagram. So the way that we could actually have this happen for a gas is so we have some sort of rigid container and then we have pressure increasing. Well, a way we could do that is by heating up the gas, so adding heat. And that would cause a pressure increase. Similarly, if we had, let's say, a process in the opposite direction, so we started here and ended here, well, then we have some sort of situation where we removed heat. So maybe we put this container of gas in like maybe an ice bath or something like that. So kind of a computational question of an isocoric situation. So let's suppose we have actually the prompt I mentioned earlier. We have pressure in a car tire being 30 psi on a cool morning when the temperature is 0 Celsius. As the day warms up and bright sunshine shines on this black tire, the temperature in the air at the tire reaches 30 degrees Celsius. So what is the tire pressure at this temperature? All right, so first listing what we know. We know our initial pressure, so I'm going to call all my initials with subscript 1 and my final with subscript 2. So my initial pressure is 30 psi. All right, now something to note here, when you're measuring pressure in a tire, that's going to be gauge pressure. So I'm going to convert that to absolute pressure by adding 1 atm, which is 14.7 psi, giving me a total value of 44.7 psi. And I start with the temperature of 0 degrees Celsius. I need to convert that to Kelvin. So that's going to be 273 Kelvin. Other information, I don't know my pressure at my finals. That's what I'm trying to solve for. But I do know the temperature is 303 Kelvin. And I also know that for a tire, the volume of the tire is not going to change. The volume is constant. And also there can't be added or removed gas. So that is constant as well. So looking at my ideal gas law, again, in this situation, N, R, and V are constant. So rearranging this, I end up with P1 over T1 is equal to P2 over T2. So since I'm solving for P2, I could just need to cross multiply by temperature 2, and I end up with this expression here. So in this expression here, right, my Kelvin cancel out, so I'm just left with PSI and a value of 49.6 PSI. So this is the absolute pressure, and it's in units of PSI. So then, converting back to gauge pressure, our gauge pressure is going to be 34.9 PSI. We can also have processes be constant pressure. This is known as isobaric. All right, so just think, all right, barometers measure pressure, so isobaric is constant pressure. So in this type of process, the pressure is going to remain constant. So if we're looking at a PV diagram, that's going to mean we have this process represented by a horizontal line since pressure is constant. One way, and then the way this could happen would be if we had some sort of container of gas in which there's some sort of movable piston. Right? The reason that's important, it means that our container of gas can have a volume change. Right? So our volume is able to increase, and while it's also heated up, then if this is done in such a way, such a magical way, it's not really magical, but such a precise way in which if we're dealing with the ideal gas law, it's done kind of proportionally enough for this to occur, for pressure to remain constant. We can also have a process in which temperature remains constant throughout the process. So this is known as isothermal. So these, if we're looking at a PV diagram, are actually always going to be hyperbolic curves. All right, so why are they going to be in the hyperbola? We see that from the ideal gas law. We have the quantity of P is equal to nRT divided by volume. All right, well, since we're dealing with constant temperature, N, R, and T are all constant, so we have P is equal to some constant divided by volume. So P is equal to some constant over V. So that means P and V are inversely proportional. So we end up with this inverse function of order 1, or is it order -1? I don't remember how you say orders, but anyway, we end up with then a hyperbola. All right. So these types of curves are also called isotherms. So if you have a graph and it says it's depicting an isotherm, that automatically tells you that in that graph, we've got constant temperature throughout that process. All right, so how can this happen? We could have, let's say, isothermal compression occur if we have, again, a container in which volume is able to change. So maybe we have like this movable piston, and maybe it's submerged in some sort of ice bath in which then the pressure is able to change in such a way that it cancels out the change of the volume so that temperature remains constant. All right. We could also have kind of the opposite situation occur, being called isothermal expansion. So in this graph here, right, we've got 3 different isotherms, but we do not know the direction of the process. We don't know whether these gases are contracting or expanding because there's no arrow here. Whereas in the graph above, we start at this kind of at this state and ends at this state, in which here we have isothermal compression because the volume is decreasing. Now, something you may have noticed about some of these processes is that we've had to have maybe adding or removing heat to the gas is changing its size, we have pistons moving, so we do have something going on with work in some of these processes. So in the next video, we'll kind of focus a little bit more about the amount of energy added or removed from our system and how we can use PV diagrams to help us actually compute that.